My greetings to everybody, and I would like to thank those who helped us organize this meeting. The subject I'm ready to familiarize you with is studied by such a branch of physics as mechanics. To illustrate the importance of this subject in question, I would like you to consider the following. A human being is always faced with two global threats which we would not eliminate. I'm talking here of a threat to human health posed, firstly, by various diseases, and secondly, large-scale natural and man-made disasters. To be able to withstand health threats, humans need to have strong immunity, which is an integrative health status indicator. In the field of mechanics, we may also talk about a characteristic property whose role is akin to that of immunity for living organisms, and that is mechanical strength. In case all man-made objects happen to lose their mechanical strength, humans would perish, either ending up under the rubble of collapsed buildings and bridges, or due to explosions at nuclear power stations, or in plane crashes. For the use of all these constructions and mechanisms is dependent on their natural durability or resistance or mechanical strength. So, to reiterate, if we take care of our immune system, trying to boost its strength, we should also make sure that the environment we live in is mechanically strong, since its insufficient mechanical durability may put our lives at risk. Mechanical strength is based on physical properties of materials and structures created from these materials, and everyone is familiar with the way durability or strength manifests itself. We know, of course, that if some mechanism, like a car engine, for example, starts vibrating in an irregular manner and roaring too loud, we may expect it to break down and cause an accident. The worst-case scenario would be an explosion. This is relevant for all power units such as engines, electro and nuclear station turbines, actuation systems of aircrafts and naval vessels, as well as man-made structures that are seemingly static. However, they are static only until their durability level exceeds impact. As soon as mechanical strength of edifices and bridges is reduced, they may collapse, and the consequences of such destructions are extremely disastrous. Some of you may remember, to name but few, the Chernobyl nuclear accident and Sayano-Shushenskaya hydroelectric power station accident, which led to large-scale disasters. So, the process of stress load impacting durability or mechanical strength of a given object is expressed through energy released by the said object. And, as a rule, this energy is expressed through vibration. If there is any vibration, oscillation or tremor, all of them being synonymous terms, we deal with a physical process signaling resistance of a structure to some impact. This process is referred to as state. The state of an engine, bridge, state of pylon or bearing piece, state of an automobile. And since our meeting is taking place at the Transport and Communication Institute, which is historically associated with aviation engineering, I would like to start with an example which is meant to make you ponder on whether everything is fine with all the means of transportation we use on land and at sea. The following fact should give us food for thought. Aircraft engines are known to be among the most accident-prone technical systems on board, and it is commonly accepted practice to measure levels of their vibration with the help of monodimensional or 1D sensors or vibration transducers. It has been customary so far, as the level of accumulated knowledge is not allowed to measure oscillations in a way they really occur in nature, namely as spatial, multi-dimensional phenomena. You must have heard of such a term as vibration spectrum, used when dealing with vibrations of different frequencies. Have a look at this rostrum, for example. It is vibrating from the sound of my voice and the steps made by the man entering this room, and due to the noise and vibrations caused by the traffic outside. All these various vibrations are being distributed in the space, and 1D measurements would not reflect this multidimensional spatial phenomenon in its whole complexity. Let us now have a look at the aircraft engine. You see a broad frequency spectrum from 0 to 15 kilohertz in this diagram. It depicts the level of oscillations amplitudes, or in other words, the power of vibrations. And the highest amplitude occurring in this field has drawn the specialist's attention as a signal of potential failure threat. You may see the signal highlighted in a red box. When an engine is being designed, the designer-in-chief identifies the vector of most dangerous vibration. The engine is usually viewed as a rotor power system resting on two supporting elements, and the designer-in-chief mounts vibration transducers on both supports to check if vibration is within the norm. If the level of vibration is higher than normal, adequate measures are to be taken. However, if we consider vibrations at the measurement point along other vectors, apart from Z, a spatial component identified by the designer-in-chief as the vector of most dangerous vibrations to be monitored during the flight, we will see that the values of other two spatial components or vectors exceed the value of the component monitored during the flight. Now, why is the engine still working, keeping the plane in the air? Because the aircraft reserve factor is very high. If not for that, the engine would break down. This, however, should raise our concern, because a pilot monitors only the level of one vibration component or channel during the flight, whereas there are two more of such channels. Here you see the second channel of vibration along the tangential vector Y, showing a so-called lateral vibration, which is not measured during the flight. If vibration in the conventional channel Z equals 4 acceleration units, it amounts to 7G in the lateral vibration channel Y of this particular aircraft engine. The situation, however, is even more dramatic with a third actual channel in the same frequency. Here you see the magnitude of vibration shown by a small red box. The magnitude of vibration reaching 11G. Now, applying the Pythagorean theorem, we can calculate the real vibration level. So, the real vibration is 14G, that is 2.5 times larger than the one shown by the sensor assessing the performance capacity of this particular engine. Such situations are very common and widespread, and can be explained by lack of equipment capable of measuring vibration in space. Now, what is the physical nature of the threat posed by vibration? Let us imagine a resilient or elastic rubber-like cylinder and observe the changes it will undergo upon normal, harmonious impact acting along the axis of the given cylinder. So, at the n0 point, the impact equals 0. At the next n1 point, there is already a certain positive value characterizing the impact, 0.7 of a maximum value. And the third point that shows the maximum oscillation amplitude, here it's indicated by a small arrow. And increasing the stress load results in the reduction of the cylinder height. It collapses under the normal impact of the force applied, and at some point the cylinder will take a tub-like shape. It is clear that there is a limit for compression. At some point the material will burst. What we are dealing here with is a reserve factor or safety margin for construction, or durability or resistance to stress, which determines the domain of linear oscillations and elastic deformations. And resilience or elasticity is a physical property of a body or material to return to its original shape when the stress load is relieved. And it is resilience or elasticity which gives physical meaning to the concept of durability. Durability persists until the body or material has lost it. Thus, while the top of a table, for example, is resilient. The table serves its purpose. If, however, we put something on it heavy enough to overcome the table's resilience, the table will break down. This analogy may sound oversimplistic, but it is still quite fair. So, what is the essence of this phenomenon? Impacting the cylinder along its vertical axis, or in other words, giving it a normal impact, the object changes its geometry in perpendicular plane or in tangential direction. Thus we impact the object in one direction, but the effect of the impact manifests itself in a different plane. Now, what does all this imply? It means the following. If we take our measurements with the help of a 1D sensor, we do not see the aggregate component which squashed the object, preserving its resilience or stress resistance. We proceed from the idea that all natural processes having spatial properties are to be measured spatially as well. The procedure is really straightforward. Just take your textbook in mechanics, which you used to study sitting for your high school or college exam, and let's see what it says. It says that full oscillation or full vibrations consist of a linear displacement and rotational one. In other words, full oscillation or vibration is an aggregate phenomenon comprising linear rotational elements. And measuring linear displacement, we have to take the value of its three components, x, y, and z. And in the same way, to determine rotational displacement, we measure the three vector components. These two sets of measurements are to be taken so that we can have a full picture of what is really going on with an object being monitored for safety reasons. Now, there comes the most complicated bit, and I would like you to get focused because what I'm going to tell you is very important. Natural durability or stress resistance observed in nature is referred to as natural synthesis in science. It manifests itself through the formation of a certain state of an object under the impact of different forces. How does it all happen? There occurs an external impact getting through the shape and material of an object multidimensionally. Now, let us specify what multidimensional impact means. In the previous slide, we have seen how vertical impact causes reaction which is distributed through the whole object in all directions. This means that transformation from normal impact to spatial deformations happens tensorially, or in other words, multidimensionally, and in accordance with the matrix, three strain coefficients x, y, and z develop into three deformation coefficients x, y, z. The relationship between strain and deformation is that of cause and effect. The strain realizes itself as distribution of forces inside the object, and it is invisible as such, whereas deformation caused by the strain can be observed. Thus, in the case of our cylinder, we see these deformations, but they may also be so small that to register them just with the naked eye would be impossible, as for example in the case of metal parts of an aircraft engine, but sensors or transducers mounted on the aircraft engine are meant to measure such deformations. The problem here is the following: to be able to measure them in full correspondence with the way these deformations are caused by natural forces, triggering oscillation processes. Our transducers have to be able to restore the whole process in the reverse order. We need to measure deformations through the reverse tensor matrix, thus assessing the state of stress resistance. That is the task of the analysis. Now, the main idea I would like you to remember as a take-home message is as follows. Any work performed by nature is done spatially in 3D and simultaneously. Now let us turn to theoretical mechanics, which is 300 years old. By the way, all I'm talking about here has been known for 300 years, although for the same 300 years they have had no methods to take vibration measurements as they would occur in nature. So, there are theorems in mechanics that describe the law according to which strain is formed, and there are theorems describing the law under which deformation occurs. Both strain and deformation manifest themselves in accordance with the so-called elliptical law. It means that all oscillations in any material or object occur along the same trajectories that characterize movements of any space bodies and are governed by the same law. We tend to take it for granted that planets of the solar system move along elliptical trajectories. I strongly believe, and I'm going to show you a film later which will prove my point, that all vibrations that may ever originate, including vibrations created by my voice, spread along elliptical trajectories. If we learn to measure vibrations properly, we'll be able to observe the elliptical shapes they form in the environment. This scientific research work was commissioned by the Gazprom. The goal set was to assess the difference between standard vibration measurements taken at gas compressor units with the help of 1D sensors and those taken with the help of our 3D transducer. The thing is that gas compressor plants are quite dangerous to operate. To prevent threats, it is important to check up the state of such a unit. So, the crossing coordinates represent a 3D space. The third coordinate is directed towards you when you look at this diagram. A standard 1D sensor positioned at this point and have its own direction will measure vibrations as it is shown here in green color. Now, what does a spatial sensor or vector transducer measure? It measures the position of a point or vector in accordance with the three coordinates x, y, z at every moment in time, and then all the resulting points are made discrete by a computer program. That is, at every next moment the computer draws a point, and there are lots of such points, a whole cloud of them. So, these elliptical vibrations, whose existence was theoretically proved 3 centuries ago, have now been measured instrumentally for the first time ever, and this is what the trajectory of vibrations looks like. This elliptical trajectory is characterized by the major axis and minor axis. If we take our cylinder, the vertical impact coincides with the major axis of elliptical vibrations, and the minor one represents the force turning the cylinder into a round-shaped tub. So, the point drawn by the computer is perpetually shifting along the following trajectory around the measurement point. There is another interesting parameter which cannot be measured by a 1D sensor. It is the direction of the point rotation that proves to be of paramount importance. If the point rotates clockwise, it means the source of vibrations is located to the left, and the wave has come from there. If the rotation takes place counterclockwise, the wave of mechanical vibrations arrives somewhere from the right. And all this is important for diagnostics, because it enables us not only to determine the direction of a perturbation of a disturbance, but also find out on which side of the monitored object the source of perturbation is located. As to the source of disturbance, it can be an external force producing an impact, as well as an internal one, a crack in the monitored object, a rotor, housing body, or friction bearing, for example. This particular diagram, by the way, reflects the work of a cracked bearing cage ring, and you can see the crack here. If the monitored object had been fault-free, the ellipse would have looked perfectly symmetrical. But due to the fact that there is a crack in the part, its resistance to stress drops down, and the range of vibrations increases. So we see that the ellipse should serve as a very informative diagnostic parameter. However, this ellipse is created only on one frequency. If another frequency is present, there will be another ellipse, differently directed, and if there is the third frequency, we have to already speak of a bundle of vibrations. And lately there have appeared some French patents in the market offering devices to measure a bundle of vibrations, which they introduce as a special term. Thus, the range of vibrations is defined as vibrations bundle, and since a conventional 1D sensor is capable of taking measurements only in one direction, any of the ellipses comprising the bundle will only be measured as projections to the transducer's own axis. In other words, if an ellipse is projected to the axis of a 1D transducer, we end up having a 1D measurement of vibrations. So, where do we stand now? There have been created some technical devices allowing natural synthesis, the root cause of impact leading to damage and emergencies, to be analyzed on the basis of direct and verifiable knowledge through the reconstruction of vibration waves. For taking measurements in real time, the said technology needs to be supported by a computer program, and thus it incorporates the IT element. When there was no access to such knowledge and technology, various man-made disasters used to happen, like the one at the Sayano-Shushenskaya Dam on the Yenisei River, for example, where the state of the operating block had not been monitored on a permanent basis for resistance to stress. Thank God the dam itself did not explode, otherwise all those living in the river basin below the dam would have lost their lives. Now, concerning the second aspect, I would like to draw your attention to. It is quite interesting and demands of some basic knowledge of mechanics, but I would like you to make an effort, since this matter is also crucial for the technology we are offering. While at school, you must have studied the Hooke's law. It describes the relationship between a force applied to an object and its deformation. Deformation in an elastic object increases linearly with the force till the limit of elastic behavior. Until reaching this limit, an elastic object will return to its original form if the force acting on it is removed. Beyond the limit of elastic behavior, deformation is irreversible and the object is destroyed. So, the Hooke's law is depicted as a linear diagram with the linear part ending at a point when the material loses its elastic properties and the straight line of the diagram bends. And all machines and constructions and their elements are designed in such a way so that their elastic properties are not lost in operation. That is, they have to stay within the linear part of the diagram. And all machines and constructions and their elements should have a certain safety margin. In buildings, the safety margin has to be from 8 to 10-fold. In vehicles, from 2.5 to 3. In case of hazardous objects, such as airborne devices, for example, the requirements are much stricter. Here you see a dimensional image of a generalized 3D Hooke's diagram. The blue field represents the Hooke's law. Look at this bend. Now, what are the coordinates? Sigma stands for tension and or force per unit. Now, there is another law designers are aware of, although they tend to ignore it, the Poisson's law, which connects longitudinal or normal deformation with the shift or tangential deformation, when an impact in one direction results in an impact along a different vector. Remember the tab which our cylinder has turned into. Now, we have realized that these two laws, Hooke's and Poisson's, constitute one general mechanical law describing spatial properties of an object or material to experience deformation due to external forces. This spatial law can be applied to define and calculate the safety domain for the operation of an object in question. This new knowledge gives an opportunity to create spatial software special software for automatic monitoring of a device or construction, with an aim to see if it is operating in a safe mode. So, the law of Hooke-Poisson is actually old news. Each of the separate laws is 300 years old. Yet, without computer technologies, it was impossible to present and realize them spatially. And this is another innovative element of the method I am telling you about. This is a simple poster demonstrating elastic behavior of an object which returns to its original form after the force acting on it has been removed. And to the right you see the object already in its plastic state, when it does not return to its initial form after the removal of the force, which serves as an indicator of the existing threat. Now, let us unite the two facts I have been sharing with you. We understand that all deformations have elliptical character. We can measure them in 3D. Now let us try to analyze how the position of a measuring instrument depends on a point and direction of an impact. The following diagram may serve as a good illustration here. Here you see the vector oscillating harmoniously to and from the 0 point. Depending on where we mount a 3D transducer, we obtain different shapes. Here the first position of the transducer at the angle of 15 degrees coincides with the direction of the normal force impacting our cylinder. The second position is at the angle of 40 degrees and the third one at the angle of 75 degrees. That is, depending on the angle between the vector of the impact force and the point where the transducer has been mounted, the shape of the ellipse changes. And if we repeat this experiment with the same initial data after some time, be it a day, a week, or a month, the picture will be the same. In other words, what we deal with here is a consistent pattern. And so all this means that we can, so to say, teach the computer to analyze the shape of an ellipse, position of axes in space, correlation of these axes between themselves, as well as the angles at which the ellipse is positioned in space, and on the basis of all these data receive full and comprehensive information on the stress-deformed state. And again, we are talking here just about one frequency. At any frequency we will receive a set of analogous pictures. And it is clear that a person operating a device, a test pilot, for example, won't be able to fully assess the stress. Only a computer, due to its incredible computational capacity, will be able to register and measure all this in real time. It is noteworthy that until the 21st century, even such monsters as Hewlett-Packard were unable to record these mechanical measurements in real time. Processing of all data would take more time than measurements themselves. And it is only now that this drawback has been overcome. In this picture, you see an element of a power turbine. The unit weighs 200 tons. So, you can imagine what it is like. It rests on 4 supporting blocks. And if its vibration exceeds the permissible level, there may be an explosion resulting in a terrible destruction and loss of life. So, we have conducted the following experiment on this unit. The upper point I'm showing you is a vibration measurement point pre-calculated by the designer-in-chief as the most dangerous one, and there is a bearing installed in this place. The most dangerous vibrations are expected to occur at this point, and accordingly, if measurements are taken here, then it should be clear how to further analyze the data statistically and what preventive actions to take. Now, what was the essence of the experiment we performed on the turbine? We first measured vibrations at the pre-calculated point with the help of a 3D sensor, and what we got was an ellipse. In other words, instead of measuring vibrations in terms of voltage, where we would receive the value of 2.5 volts, for example, we received an elliptical trajectory which had nothing to do with the voltage. Then, assuming the designer-in-chief might have miscalculated the measurement point to mount the sensor on, we decided to position our 3D transducer somewhat lower, and it turned out that the ellipse formed at the second point had a totally different character. Its deformation in the transverse plane was much higher. Then we checked another point, moving all the way down to the supporting block, and we saw that the direction of vibrations in the third point changed dramatically. Then, having moved downwards, we decided to measure vibrations at any given point along the bottom of the unit. So, now you see in what way parameters of vibrations change depending on where the transducer is positioned, if we measure them spatially with the help of a 3D sensor. If, however, you monitor vibrations with a monodimensional sensor, you will receive the same data at any given point. So the advantage of a 3D transducer is obvious. The information we gather is much richer. That is our practical work. As well as in the case of the aircraft engine we discussed earlier, you may see here at this particular turbine generator frequency the 3 components of vibrations. The next experiment, which proved to be very interesting, was set in connection with the task to discover a missile targeting an aircraft. There are 2 radars installed at a given distance between each other, and proceeding from the angles at which the missile has been located, we can draw a triangle identifying at which point the missile is at any current moment. This procedure is called triangulation. Bearing all this in mind, we decided to check another idea. Our sensor feels where the wave is coming from. All we need is to determine the direction of the elliptical movement, so that we can identify where the source of vibration is. Thus, while doing our research for the Gazprom, we carried out another experiment. We mounted 4 transducers on the turbine generator. We believed if our assumption was incorrect, the vectors would not all converge in one point. Yet our assumption proved to be accurate. The vectors of 4 transducers converged in one point, which really appeared to be the source of the unit's vibrations. There was a crack there. It turned out dangerous vibrations were caused not by an external force, but by the crack, reducing the structural durability of the turbine. The fact that the big axes of all the 4 transducers converged in one point led us to an assumption that we would really need only 2 sensors to monitor the state of the unit. There is one condition, however: they have to be positioned on different plane surfaces to be able to locate the vibration source point. The technology I have been talking about cannot be realized without the information component. Now, specifying in some greater detail what our work consists of. Here you see how one of our sensor devices looks like. It carries out monitoring of elliptical trajectories. The theory underlying this technology is expressed in terms of elliptical equations. But apart from this device, we need to have 3 more components: knowledge, possessed by a researcher or operator, experience gained by them, and intuition, which is especially important for a researcher, since it allows to pay attention to some phenomenon which will enable forecasting and which leads the way to new knowledge. All this is the basis of our work.